All right, so good morning, everyone. Happy Monday of what looks like a fairly stressful week with the election coming up. So I just wanted to address that before we start and say that, if you're dealing with a bunch of stress, or if um, if you need anything that I can help you in terms of at least alleviating the stress within this class, please reach out. So I just know that everybody I talk to is very stressed out right now. There's a lot going on. I will throw out there that I will hold. So every Monday I do Mindful Monday at 12:30. If you want to join today, we're gonna essentially try to lower our anxiety due to the election. Um, so please feel free to stop by if you want to participate. And you can just stop by. Usually, I have some relaxing music if you don't want to. You don't need to turn on your video or anything like that. Um, and so I just wanted to address that. And I know, that's why I sent the announcement yesterday about moving the homework deadlines. So I just want to also be mindful of the fact that you have a big deadline now with all these homework assignments. So I would really encourage you to still work on the homework weekly as the videos are getting rolled out, and and to help with that, I figured what we could do during our weekly meetings is actually go over the assignments together. So, and of course, if you want to bring up anything during those meetings, something else that you would like to talk about, we can absolutely address other things. Um, so before we started the meeting, I had a question actually about the final. So I wanted to share with everybody. It was in terms of how many questions. So I don't know exactly, but it may be a little bit longer than a midterm, but not by all that much. The big difference is that it will be cumulative, but it will have a large emphasis on the on modern physics, because that was the part that was not covered, that will not have been covered in the other midterms. So it will be heavier on the last unit. I mean, an option is to have a midterm for the last unit followed by a final, but I feel like that's a little bit too test heavy. So instead, that's going to be incorporated in your final. Because of that, there may be more questions, but not, it's not going to be like double the midterm or anything like that, because I know, again, we're in an online environment. I don't want you to be online for a few hours in a row and just assume that you can do that. I know it's not necessarily possible. So I want to be mindful of all of this. And if you do have any concerns about it, please let me know. Um, so before we get started with the next homework and assignment, again, that is now due at the end of November. So this is all on purpose, but we can work on it together right now. But before we move on to that, I just wanted to see if you had any other questions that I should address before then. So you have, so how many exams do we have left? So I'm going to show you actually on Canvas, because it's going to be a little bit easier. Um, Actually, so I'm going to show you my view. Okay, here we go. So on my view, I have kind of things set up that you can't see yet because I haven't published them. And so we covered Unit 1, Mechanics 1. So that was for each unit, you have a midterm. So then we have Unit 2, Mechanics 2. So that's what you just completed, all right, with the midterm last week. We are starting Unit 3, Classical Physics. In that unit, we're going to talk about thermal physics. So we're going to go over the questions on the homework, on that homework now. It's going to cover electricity. I'm working on the videos for that, so you can see like some of these things are not published yet. Magnetism, in light. So at the end of that unit, which is going to end at the end of November, you will have a midterm also. And then there is one more unit, which is modern physics. And I can open that up also soon. So if for any of you who want to get started. So with modern physics, we'll talk about quantum mechanics, special relativity, nuclear physics, and there's not going to be a midterm at the end of this one, and that's because you're going to have your final essentially right after. So that's essentially a test that combines modern physics but also the final, so it's going to be cumulative. So the answer to the question is, how many exams do we have left? So we have one midterm for unit 3, and then we'll have a final. All right. Okay, so I'm going to go back to student view so that I don't click on something on accident that you shouldn't be seeing. And I also want to go back to the chat, and I just want to make sure I answered your question. Okay, so one more midterm and then the final. Any other questions? And again, you can type in the chat, or you can also unmute yourself if you prefer. All right, so I have not had a chance to look at your midterms yet, so don't worry if the scores have not been updated yet. I will try to get to those as soon as I can. Last week was particularly crazy. By the way, actually, while I'm here, I also want to mention that you should be seeing a student evaluation for me, that if you could please make sure to complete that before the deadline. So this is something that we do regularly, and in fact, so I've been teaching for a long time, but I started at Skyline full-time last year, and it's part of my tenure process. So if you can please give your feedback. I think it shows up in, I don't remember if it's in Canvas or WebSmart, but you should be getting a notification that you need to fill out a student evaluation for me. So if you can make sure that you get to that. When are the discussions going to be graded? So again, I'm working on, it's on my to-do list, and I'm going to try to get to that as soon as possible. It's definitely been a struggle to keep up with everything, to be very honest. So it's a hard balance. Last week, and I'm not saying that to complain, but Thursday and Friday I worked till 5 a.m. to just keep up with the workload, and so it is up there on my to-do list, and I'm gonna try to get to that as soon as possible. And that's the case for anything that needs to grade. I will very much admit that I am behind on grading, which I feel really bad about, actually, because, and I don't want you to feel bad about asking that question at all. It's totally legitimate. Usually I have a rule that I give myself 1 week, and I've always done that my whole 10 years of teaching. Within 1 week you get everything back, and this semester it's just been crazy. So, but it's definitely on my list, so I will try to get to that as soon as possible. And so what I wanted to do today is, so if you look at the thermophysics chapter, so you have now all the content and the videos. You do have a discussion that's due this week. So I have actually not moved the deadlines for this discussion. It was just to kind of keep a guideline of when you should be looking at things. And so there's a lot of text to read here, but you don't necessarily have to. And I just wanted to also maybe give you a chance. So we can go over the homework question. I think maybe that will help. And then maybe give you some pointers, or maybe we can discuss how to post something about this, because this one is due on Wednesday. I can change the deadline, but The idea here is that so we talk about engines, heat engines, for example, in this unit, in this chapter, and you can think of the of your own body as something that is, you know, you're eating food, and so that means that you're getting some energy like that. But you're just to stay alive, you know, your body is doing a whole lot of different things that do require energy. And the idea was to think about, you know, the energy that is the intake. So how does that look, and the energy that is being used, and you know, the work done by your body, the different heat transfers that are happening. And so the idea was for this discussion, and so again, that's why there's kind of a lot of words here, but to talk to somebody, and it could be somebody in the class, or it could be somebody you know, and just in a typical 24-hour period, just looking at the energy that is being used and the energy that is being gained, you know, through food and things like that, and look at the intake versus, you know, what's being used, and to think about what for each source of energy or for any energy exchange that is happening, how does it fit in the first law of thermodynamics? Okay. And we can go over that discussion together, but maybe to help with some of this, we can go over some of your homework questions together. So, so you can see that the line is now November 23rd, but it doesn't, but you should really get started before then. So what I want to do is not necessarily just, you know, give you the answers, because then it's kind of pointless, but I want to just start this and do have some discussions about those questions. And also, you know, if you've already started, I can address any question that you have. So right now you're seeing the first question, and I just wanted to see, go over this with you and see what your thoughts are. Um, okay, and so, and again, to facilitate discussion, feel free to unmute if that's easier. And I have too many things on my screen. Okay. And so the first question is a temperature question, and in particular, it's talking about the Kelvin scale. So it could be, you know, if you haven't had a chance to look at the material, it may sound a little bit foreign, but that's okay. So the Kelvin temperature scale is special in that it is the only absolute temperature scale in use. By absolute temperature scale, we mean that the 0 point of the Kelvin scale has a significant physical meaning. Compare this against the 0 point of the Celsius scale, which is the melting point of ice. But why should ice or water have such a special role in defining the 0 point? It is for this reason both the Celsius scale and the Fahrenheit scale are relative temperature scales. So it's a lot of words, but do you know where we're getting at? So here it tells you to choose all statements below which correctly state the physical meanings of the 0 point of the Kelvin scale, 0 Kelvin. So the thing that is absolute is interesting because of various laws of thermodynamics that we have. Do any of you, so looking at the different answers that we have here, does anything look like something that looks correct or relevant for this? So, okay, so let me read that. So you just see the email. Okay, I'm showing you the wrong screen then. Oops. Thank you for letting me know. Okay, I meant to show you this. Are you seeing the question now? Sorry about that. I was sharing the wrong screen, I guess. Okay, thanks for letting me know. Okay, can you see the question now? Okay, cool, thank you. All right, so I read the question already, but then you have the various answers. So you can also follow along with your own, in your own canvas. So at the 0 point of the Kelvin scale, we find the coldest temperature ever reached on Earth. At the 0 point of the Kelvin scale, a hypothetical gas that remained in gas phase has zero pressure and zero volume. The 0 point of the Kelvin scale is the temperature of the cold, empty outer space. The 0 point of the Kelvin scale is where all microscopic thermal motions come to a stop, or the 0 point of the Kelvin scale is where we find the triple point of an ideal gas. So maybe if you find a statement and you see something wrong with the statements, maybe you could share with the rest of the class. And you can do that in the chat and I can read your answer. Or if you can identify the correct statement, you can also tell me. And so we can see in that order, you can type a number too. So if you can say 1, 2, 3, 4, 5 for your correct answer. But we can also try to point out or try to eliminate the answer that would look incorrect. So what do you think? Anything that does not sound quite right? Because sometimes we have to do this by process of elimination. I mean, it could be that, oh, it's like, oh, maybe it's between these two. And then we can have a more of a discussion about that. So what do you think? So we can start, let's start with the first statement. So at the 0 point of the Kelvin scale, we find the coldest temperature ever reached on Earth. Does that sound right? That's false. And as it turns out, the third law of thermodynamics actually tells us that we can never reach that 0 Kelvin temperature. So there's no way we'd have actually experienced that on Earth. So the first statement is incorrect. Thank you. All right, so the second one, in the 0 point of Kelvin scale, a hypothetical gas that remained in gas phase has zero pressure and zero volume. All right, does that sound correct, or is there something off with this one too? And sometimes it's tricky because it's one word. That's correct. So it's false also. So the word that's incorrect in this one is volume. So technically, if we were to see a gas that would have a temperature of 0 kelvins, it would have zero pressure, but also zero temperature, not zero volume. So that would be incorrect. All right, so what is the temperature? The temperature of the cold, empty outer space. Is that correct or incorrect? And you can all, jump in. And we're getting down to 3 statements now, so. And I kind of gave you a big hint when we answered the first question. That's incorrect also, thank you. Because I just told you we can actually not reach that temperature. So it doesn't matter where you're at. So the 0 Kelvin is not something that is doable. All right, so we have 2 statements left, 4 or 5. Which one is correct? So if you can type in the chat and we can see if you think 4 or 5 is the correct statement. So we're down to 2. All right, so we have 1 vote for 4. Does everybody agree? And you can also just give a thumbs up if that's easier. If you agree with Ethan that it's number 4, yes. So yes, you're correct. So 4 is the correct one. So essentially, what is the 0 Kelvin? So the Kelvin scale is important because it's on this absolute scale, and it's because the 0 Kelvin Um, you got two correct. Um, oh, you're correct. Sorry, I read that wrong. Thank you so much, Samantha. Now I'm confusing everybody. Because I read it as if there was one statement, but you're right. So we have two statements that are correct, and you're right. So number 2 and number 4. So sorry, that's my bad. I read that wrong. So the Kelvin scale is such that the absolute zero is the lowest value that you can get. So you cannot get to any temperature that's lower than that. And that's because by definition, the 0 Kelvin temperature is for essentially when so it tells you where all microscopic thermal motions come to a stop. So that means that nothing is moving. So if you were to zoom in and look at your molecules, everything would come at rest. There would be no motion, there would be no energy. And so that's why the Kelvin scale is important, because it tells you that you can never get, so there's never going to be a negative temperature in the Kelvin scale. For the Celsius scale, however, so we set the 0 to be the melting point of ice, and it's kind of convenient because those are temperature that we, if you look at the weather patterns and things like that, it can be interesting to see, okay, if you have a temperature below 0 degrees Celsius, then you know that you're going to be looking at something that is, freezing temperature. But there's no, it's not absolute in the sense that it's arbitrary, because we just used water as a point of reference, but we could really have used anything else. You know, thanks for the correction. I'm glad, because I was, for some reason, see, it says choose all the statements. So as I always say, you should read the questions carefully and read them several times. So I just zoomed in on the one that I knew was correct, and I totally forgot that you could actually use several options. So 2 and 4 in this case. And the fifth one is also incorrect, because it talks about the triple point of an ideal gas. Again, that would not be something absolute, because that's something that depends on the gas that you're using, or it's something very specific. So, but I just wanted to go over this, because this is important in terms of how we go over these concepts of energy and temperature. Is that really the temperature of a system measures all of the motion of the molecules. And so the more motion you have, the more vibrations you have, the more energy you have contained in your object. And the greater the temperature is going to be. So really, when we talk about something that's hot or cold, something cold means that there's less motion of the molecules, versus something hot, there's more motion, and you're gonna, so if you put your thermometer there, you're gonna see a greater reading. All right. So I know there's a lot of questions, and I want to go, and you can pick some questions if you tell me, like, oh, we should, oops, what am I doing? Wrong button. Okay. Can you tell it's Monday? And okay, question 2. All right. And yeah, if you tell me, okay, there's too many, we can skip this one, please let me know. I don't want to waste your time. Okay, so this one talks about ideal gases. And so when we deal with ideal gases, we have this ideal gas law. You can see it in different forms. This one is PV equals NKT, where N is the number of molecules. Sometimes you'll see it with the number of moles, and if you've taken chemistry, there's different ways, different units that can be used. So in this equation, we have P, which is the pressure of the gas, V, which is its volume, and the number of molecules. K is a constant. It's the Boltzmann constant that is given over here. And then you have T, which is the temperature of your ideal gas. So the question is, so we're given this equation. We want to find the number of gas molecules if the pressure is 75 kilopascals, the volume is 1.5 cubic meters, And the temperature is 279 kelvins. So the first thing I want to bring up here is the fact that we have to be careful with the units that we use. So in this equation, so you can see that if you look at K, it's given in joules per Kelvin. So we should be using a temperature in Kelvin. So we're lucky. The temperature was given in kelvins. We don't have to convert that. So 279, that's going to be our T over here. Okay. K is already set. It's given by this equation. Now, P is given. So that's the pressure, 75 kilopascal. So just be careful because the units is the pascal. So I'm going to type that in the chat, but that means that for P, we should use not 75, but it's 75,000. Okay. And the volume is 1.5 cubic meters, and you may all have been given different numbers because I think it's all randomized, but in this case it's 1.5. It's given in cubic meters. For this one, we do not need to change the units at all. So it's already converted for us. So the only thing that we had to convert was the pressure. Okay, so I'm going to type that in the chat. So PV equals NKT. And what we're solving for is when we want to find the number of molecules. So that would be N. So we have to rearrange the equation so that we're solving for N. And so I think I worked out one of the examples that does that. So it's figuring out the number of molecules that you have in your room, for example. So I just want to write in the chat because I want to keep all of I could also put it in I could use the whiteboard, but that way you can still see the question. So if we're solving, maybe somebody can actually also help me out here. If we're solving for N, what is gonna equation for N in terms of PV, K, and T? And you can type it in the chat. So as you can see, we want to eliminate K and T from the right-hand side of the equation. So what we should do is divide both sides by KT. Okay, so since it's a class where we don't want to do too much math, I'm going to show that to you. So N is going to be equal. So if we're solving for N, it's going to be P times V, pressure times volume, divided by K times T. Okay, so I'm not going to type up everything in my calculator, but if we take our pressure, which is 75,000, we multiply that by our volume, which is 1.5, and then we divide by our Boltzmann's constant. Just be careful because that's a little bit trickier to type in because we have 10 to the negative 23. It's a very small number. And then we also divide by our temperature in kelvins of 279. We should be finding the number of molecules. Just be careful in the number of molecules. You can see that it's given at 10 to the 25th. Okay. If we look at the hint, it just points you to them. So do you have any questions about this one? All right, so we just want to rearrange and solve for the number of molecule N. All right. Question 3. Okay, so that's another one where we have to choose all statements. And we will have to actually pick a few. So although they are distinct processes, heat transfer and work done can produce similar effects, as demonstrated in Joule's experiment. Choose all statements below which correctly compare and contrast heat transfer with work done. All right, so heat transfer does not result in macroscopic displacement of object, while work results in a displacement. Heat transfer occurs spontaneously from a hot object to a cold object in thermal contact, but additional specifications are needed to know whether work will be done. Both heat transfer and work move energy from one object to another. Both heat transfer and work change the form of the energy involved. And heat transferred raises temperature of the object, while the work done cannot raise temperature of the object. Okay. So is there, so again, we can say it's like 1, 2, 3, 4, 5 for the statements. So can you, so, and you can post the ones that look correct to you, and then we can maybe discuss. And again, no pressure. Some of these, it's tricky, right? They're very close, and it's not really clear necessarily what could be wrong in the statement. All right, I'll give you a hint that I think I see 3 that are correct. So I see 3 correct statements. So that helps maybe with your odds of getting them correct or not. If we go back to the very definition of work and heat energy, there's one statement to me that stands out. Because when we introduced work and when we introduced heat energy, we essentially talked about a transfer of energy. And the idea is that they are used to move energy from one object to another. So one statement that I see would be correct, and maybe that's the easiest one, is that both heat transfer and work move energy from one object to another. Yes. So 3 is correct. There are 2 more. So 1, 2, and 3. Does everybody agree? I agree. So 1, 2, and 3 would be correct. So if we look at that, right? So heat transfer does not result in macroscopic displacement of object, while work results in a displacement. So when we looked at work that was being done by a force, in order to have work done, we had to have displacement. And that's not the case for heat. So heat does not displace objects. And then for the second one, heat transfer occurs spontaneously from a hot object to a cold object in thermal contact. So we know that's true, but additional specifications are needed to know whether work will be done. So that is correct. So 1, 2, and 3, good job. All right. If you want me to skip over and to some questions, because I'm just going through each and I don't know if we'll have time to go over all of them, but if there's some specific question that you want me to go over, please let me know. All right, I think this one can be a quick one. So question 4, each of the statement below describe a property of one of the methods of heat transfer. Match them to the method of heat transfer which the statement describes. So, okay, we'll go over question 6 and 7 for sure. Can we go over this one really quick? Because I think, so we have to tell what type of transfer we're looking at. So presence of material is necessary for this mechanism of heat transfer, but there is no movement of the material. Is it radiation, conduction, or convection? So the fact, so we're told that there is no movement of the material. So if you go back to the definition, that would be convection. So convection requires a movement of material. So we know it's not going to be convection. Convection uses fluids, so either liquid or gas. So essentially how you would heat up a room. You have the motion of the fluid, so the air that's essentially moving the energy. So the fact that there is no movement of the material means that it cannot be convection. So it should be radiation of conduction. And because we need the presence of a material, it's going to have to be conduction, because radiation can happen in a vacuum. All right, let's do maybe a couple more and then we will stop. So a direct line of sight is needed for this mechanism of heat transfer. What do you think? Radiation, convection, or convection? Yes, so radiation. So line of sight is kind of the big hint there, because if you block the radiation, so it's not going to be able to go through. So we've looked at one that was conduction, one that was radiation. Can you, in the ones that are left, can you find one that would be convection? Just an example that of in the last three, do we see something that would be convection? Just to give an example of each. So in 3, 4, or 5, do you see something that would be convection? Mm-hmm. Yeah, 3 and 5, perfect, awesome. All right, and I'll let you figure out number 4. Okay, so should I skip over 5 because there were questions about questions 6 and 7? Just want to make sure. So choose the statement below which correctly defines heat capacity. So this is really a definition, so I think it's not too bad for you to look this one up. I'll give you a hint because again, it's choose the statements below. I'll give you a hint. There's 2 statements that are correct for this one. All right. Okay, so let's move on to question 6. All right, so question 6, the same heat transfer into identical masses of different substances produces different temperature changes. Okay. How much does the temperature rise when 13,000 joules of heat transfers to 1 kilogram of each of the materials below? All right. So for this one, we have to look at, so we're given water, concrete, and steel. So to be able to answer that question, so we have to use the definition of the specific heat capacity. So if you look at the hints, it's going to bring you to a table. All right. So you can see here, that's what we're going to use. Q is the heat. So you were told, in this case, it would be 13,000 joules. And then equals M times C times delta T, right? So if I go back, it's Q, which is 13,000 joules, equals M, the mass. So that's, in this case, it's just going to be 1. So we can kind of forget about that. Times C, so the specific heat that's going to be different for each material, times the change in temperature. So what we need to look for is, so in this table over here, you have the specific heat for different materials. So for example, we have what it is for water. Okay, so this is the C for water, 4,186. So I'm going to write the equation again in the chat. So we have Q equals MC delta T. Okay, so in this case, we're looking for the delta T. All right, so if we solve delta T, so if we solve for delta T, all right, so we need to take the heat, Q, divided by the mass times the specific heat. All right, we can go one step further because we're taking 1 kilogram of everything. So it's going to really be Q divided by C. So in this example, and you probably have a different number, Q is 13,000 joules. So what we need to do is look for C for water, concrete, and steel, and take 13,000 divided by each of those values. Okay, so for example, for water, I would take 13,000 joules divided by the value for water that we were just looking at, and I lost it over here, divided by 4,186. Yes. So just be careful when you put that in your calculator, because if you don't divide, so I'm going to rewrite what I'm going to put. So if you do this, you might want to do a double, like add a parentheses, because otherwise your calculator may think that you want to multiply and not divide. So something like that. Just to make sure we're also dividing the specific heat of water and not multiplying. But it should give you, if you get a huge number, basically that means that it was put wrong in your calculator. All right, does that work? And then we would look at the next one and say, okay, so then we look at the concrete and steel. So basically concrete over here and steel over here. All right, so steel 452 and concrete 840. All right, is that helpful? Does that work? Any questions? And so awesome. So the cool thing here is that given the amount of material you have, so let's say you have 1 kilogram of water, because we know the specific heat of water, and we know that if we give it some amount of energy, we're going to see a given change in temperature. In some ways, it's like when you're putting something in your microwave, or if you're putting it on the stove, you're providing that heat, the Q, and that's where you're going to see the change in temperature or a change in phase if it starts boiling, for example. All right, so I think we got question 6. All right, so let's take a look at question 7. I think there was another one. So suppose you're mixing some amount of hot water at the temperature of 75 degrees Celsius with cold water at the temperature of 6 degrees Celsius. Calculate the temperature of the mixture in each of the scenarios below. Okay. So we have, if 250 milliliters of hot water is mixed with 250 milliliters of cold water, the resulting 500 milliliters of water will be at a temperature of, okay. So when we have equal amounts, in some ways it's easier. So this is all water. So because we're mixing water and water, everything has the same specific heat. So as it turns out, if you're looking at equal amount of cold water and hot water, you're going to basically meet in the middle. So in this case, 75 hot and 6. So you would take 75 plus 6 divided by 2. But the reason, so if we think about it conceptually, we know that the heat is going to go from the hot water to the cold water, and whatever is gained by the cold water is what was lost by the hot water. We're assuming that the system is well insulated. So I'm going to write an equation in the chat. If we look at the change in temperature, just using the same, so we're going to use that same equation. So I'm going to retype that. Q is mc delta T. Okay, so there's going to be now 2 different Qs. The heat that is going to be gained by the cold water and the heat that's going to be lost by the hot water. Okay, so I'm like, how, I'm gonna just flip to I think it's gonna be easier if I do that on the whiteboard, and then that will be the last question that we'll go over, but it is an important one, and if you want to go over more of those, please stop by office hours and we can definitely go do this more. Let's see if this is gonna work. I'm not sure, but so I'm gonna stop sharing that just because it would be a little too much for them. Okay, let's see if this is going to work. No, it does not work. Okay, I'm going to try. All right, I'm going to, well, this is, okay. Okay, that's fine. I'm just going to draw with my hand, so it's going to be probably terrible in the handwriting, but so Q of the cold water. Wow, this is pretty bad. I'm like, okay, you know what? I'm going to just, okay, so Q cold is going to be the mass of the cold water times the specific heat of water. So we're lucky in the sense that I'm going to just call it C for all of them, times delta T. So the delta T is going to be the final temperature minus the initial temperature. So the final temperature, so I'm going to call that T final, minus T initial, but so it would, so I'm going to actually use the numbers so to make it a little bit easier. So for the cold water, it was 6, okay? For the Q hot water, that's going to be the mass of the hot water times C, which is the same, it's the specific heat of water, and then times T final minus T initial, so the initial temperature, which in this case was 75. All right, so for the cold one, I'm going to just put something and say, okay, this is actually heat that is being lost. So it's, anyway, so what we're going to do is say, okay, so whatever was gained by the cold water is going to be what was lost by the hot one, okay? So that means that what was gained here is exactly what was lost by this one, okay? So that means that the mass of the cold water times C times T final minus 6 is going to be equal to the mass of the hot water. And you have, I think, that same discussion in the textbook in case you're, so, and then C, I forgot my negative sign here. T final minus 75. The reason why we have that negative sign, by the way, is, so if you look at this, the T final is going to be a temperature in between, right? So in this case, you can see that it's going to be greater than 6, but it's going to be less than 75. So if we didn't have this negative sign, we would be in trouble because we would have something positive equal to something negative, okay? What is nice is that if I look around, the C is not going to matter because we're using water and water. So I can actually just remove it entirely. And then I can simplify. So it's going to be 75 minus T final. So I got rid of the negative sign. I got rid of the C over here because it's the same for both. So now what we want to do is solve for the T final. And in the first question is that if the two masses are the same, so we have the same amount of cold water and hot water, essentially the two are going to meet exactly in the middle. So you can take the average of the two values. So it's going to be 75 plus 6 divided by 2. So we have the exact amount of change in temperature because that heat was that was taken from the hot water is going to go straight in the cold water, but essentially because it's water and water, we're going to meet exactly in the middle because we have the same amount of each. Did that help, or is that confusing? And in the other questions, we have different masses. So you can see that I think it was 100 milliliters of hot water and 400 milliliters of cold water. So you can see that in that case, we have to be a little bit more careful because then the masses here will be different. So I just want to go the next step and actually solve for you for the T final. So so this is a little bit heavy on the math, so I'm happy to do this for you. And I'm gonna stop really fast. So if you have to go, don't worry, this is all recorded, so it will be posted. So I'm just solving here for my T final, and I'm trying to make it so that I have as many steps as possible. Okay, so then I'm gonna have T final of times the mass of the cold plus the mass of the hot, and that's going to be equal to 75 mass of hot plus 6. And if this is going way too fast, I'm doing that because we're running out of time, but I'm happy to go back with you later on in office hours, or you can, you know, or what I'll do maybe for this one is I'll post a video with more details because this is pretty terrible because my pen was not working. Okay, so if you solve, it looks like something like this. I think you have also an example that's worked out in the textbook. So what I'm going to do is actually work through that example in a separate video, so it makes more sense. But if you want to work it out really quick, it would look like something like this if I don't have any typos in here. Okay, so I will stop here because I know we're over time and I want to be mindful of your time. Please let me know if that's helpful at all, because I was thinking, it actually makes more sense if we walk through examples in our Zoom meetings for the next few meetings that we'll have. If it's not helpful, please let me know. That's okay. We can do also something else. So I'll post the recording, and I will add another recording. I'll put it in the content for this chapter for the solution of question 7, because I went over that very quickly since we were out of time. All right. Any questions before I stop? I want to also be making sure that I address anything that you may have. Any other questions? All right, well, thank you so much. So I'll put the recording up with the thermophysics chapter, and I will add a solution for question 7. If there's any other questions that you had problems with, let me know, and I can also post a solution for those. All right. Okay, so thank you so much. Enjoy the rest of your day, and next week we'll talk about electricity, and we'll go over those questions together. All right. Thanks. Bye.